I have the honor to introduce to you the third keynote speaker, Jim Coplien. So he's an engineer. He has a PhD in computer science from the University of Brussels. He has held researcher, professor, and visiting professor positions in the US, the UK, in Australia, in Belgium. And he also has over 20 years of industry experience and consulting experience, which basically translates to he knows his stuff, I mean, when he's talking about the real world. So he pioneered in the early 90s practical object-oriented design, and he soon realized that object orientation has its limits when it comes to taming the complexity of developing real-world software. So he became one of the founders of the software pattern discipline, which is still ongoing today with the blob conferences. And his work also inspired the Agile community, and he's now an active member of that community, and in particular is participating in the development of the Scrum methodology. And most lately he proposed the DCI, which is a novel design paradigm in which software development is modularized along interactions that interact with data from within a dynamically allocated contexts. So I could go on telling you about all the things that Cope did, but I'd rather conclude this introduction by telling you what I find fascinating about him. So whenever you ask Cope a question, he'll never answers the way you expect. And take any subject in computer science, you start a discussion with him, he'll put it in a different light. So in the end, when you walk away, whether you agree with Cope or not, you will ponder about what he said, and at least that's what happened to me last time when I listened to your keynote. And what he has to say is, intense, and it made me take a step back and reevaluate my view on software development, re-examine my way of thinking, and that's a good thing. So I hope Cope will have the same effect on you today, and I would really like you to give a warm welcome to him for his keynote.
That was fun. So that was good, except you just killed all the questions that are going to come at the end. So welcome. How many of you are having a great time here? It's an honor to give the closing keynote here. And this is one of the last opportunities for us all to be together. And I'd like to take this opportunity to ask if you consider yourself one of the organizers of this event to please stand up. Come on, guys, stand up. And I think we owe them a great appreciation for an event well run, and I'm very grateful. Thanks, guys. You've done a really great job. So let's see. I have someone else's slides here. Here are mine. There we go. And this thing is off. How do I turn it on? Or does it just, there were a lot of, oh, it's still broke. There were a lot of technical problems getting going this morning, but I hope things will come together. As has been announced, I'm more of an object guy and a process or organization guy than I am a models person. So the hat that I'm wearing today is from a perspective largely of object modeling, and I've been involved in objects for just about as long as they've been around in the industry. The title of the talk, "The Straight Line is Ungodly," is a quote from Hundertwasser, the architect. I do a lot of looking at the architecture, mainly of the vernacular world, and I've worked a little bit with some architects, like some people in the Jon Utzon crowd back in Denmark, and of course with Christopher Alexander. And I really like Hundertwasser's stuff. His statement, "The straight line is ungodly," is that, I mean, straight lines don't exist in nature. And in some sense, we as human beings are part of nature instead of being apart from it. And software always has some human element. It's there to serve some human being. And unfortunately, we try to make things unnatural. We try to put them into a framework, and a lot of this framework comes out of history and kind of our fascination with mathematics and purity and correctness. So a lot of us, I know I grew up in the United States, and when you're in kindergarten and you learn to color, you get a coloring book, you teach your children to color inside the lines. You don't dare color outside the lines. And I think that carries over into a lot of our thinking about precision and determinism. And all of these are illusions, and I think that the attempt to impose these on software design causes us a lot of pain, and this is where a lot of the problems come from. And I mean, I've been looking at the problems that you folks face here during the past week, and I think it fits this model pretty well. There's a lot of accidental complexity that arises just by the application of using a model that otherwise wouldn't be there. And what I'd like to do is talk a little bit about that today and talk about some alternative ways of doing things. Now, I'm a big fan of models, and I'll say later, I mean, there is nothing but models. That's all we've got. A program in C++ is a model. A UML diagram is a model. A mock-up, a prototype is a model. And that's all we've got. But the question is, what do we expect from a model? And what do we do with them along the way? And do we treat them as though they have straight lines? Now, the first part here is kind of a tutorial just so we can understand each other. I'm going to define some terms the way I mean them, and it's not that I believe that I'm right, but just so we can communicate, so you know what I mean when I say certain things. So I didn't put a lot of thought, maybe a couple of days of thought into this definition of model. So what is model? It's a thing. It's an artifact. And it's produced or used to support some method. So there is some process behind this by which we're going to use the model to draw conclusions. We're going to go to the model and ask it questions and try to learn something about the properties of the system of which it is a model. And if you look up the word model in the dictionary, very prominent in the definition of the word model is the word simple. And so a model should be simple, and that means that it's going to be a partial view of the thing that we're looking at. Unless what we're looking at is very simple, in which case, you know, there's not a lot of value in working with models. Now, I work with complex systems. I spent 20 years at AT&T, and I mean, it's a pleasure running into some of the other telecom folks here. Brand's a fellow telecom folk, and yeah, we had a short discussion. I mean, these systems are hundreds of millions of lines of code developed in dozens of countries and have 3 seconds of downtime a year for all reasons. They have thousands of processors and serve hundreds of thousands of simultaneous users. That's a pretty complex system. So, of course, models help us understand different parts of that. And a model is always simple. And there's this famous quote, of course, all models are lies, most models are useful. And to me, everything is a model. Now, every system is a model of itself. And we can use the system itself to gain some understanding about it by just looking at it in a certain way, or taking the system through a certain process that gives us some information about it. So, and a model doesn't have to be a separate artifact. It often is, and that's fine. We'll talk a little bit about the problems of that. the goal, as I said, is simplification. Now, we simplify as human beings in two ways. One is by abstracting. So, if I had a pile of coins here, and I asked you to sort them, you would define some criteria by which you're going to sort them, either nationality, or color, or metal, and you would ignore all of the other individualities of the coins and how they differ, like how much currency they are or their size. Or maybe you choose to organize them by size and you ignore some other properties. That's called abstracting. We also will organize things by partitioning, where we're just going to get out our knife. Now, there are many shapes of knife. I don't know how many of you have read Zen and the Art of Motorcycle Maintenance, which is one of the best books on system design that you can read. But Piercing in that book talks about the shape of knife you use to cut up a system. And we try sometimes to understand a system one part at a time, and then try to make a gestalt by understanding the whole. Now, if you go back into French philosophy, Descartes was very much of the second school, where you start with the whole idea, you break it down into parts, and then you understand the parts, and then you do synthesis and come back up the tree. And what everyone forgets is when you're done with all of that, you do what's called dénombrement and auditing. So you kind of sit and go, and just ask, does this whole thing make sense? Abstraction is evil. Abstraction means to throw away information. We need every bit of information we can get. And one of the problems that we have in the modeling community is we abstract the hell out of our systems and we throw away information, and then we try to introduce it back in at some later time, and it ends up not fitting, and we usually end up with something that's far from simple. And it's like epicycles in the early descriptions of planetary motion. Nice simple model of spherical orbits around the sun, and then you need to come back and add all of these complex things in order to explain the real observations of what happens. And the original model no longer becomes simple. Now, modeling is very visual, and I see a lot of people here kind of caught up on the visual aspect of things and visual modeling languages. And there's a lot of different ways to portray any given system. And, every brand seems to have its own way. So I kind of went through some classical pictures here and kind of tried to tag them with what kind of model is this? This, I think, is Capella. This is all Booch diagrams. How many of you ever used Booch diagrams? Aren't they nice? They're not lines, they're clouds, they're soft. They're like they could have come out of nature. They're not something that came out of a machine. And then UML came along and turned these things into boxes, and they now hand out straight rulers and pens at modeling conferences to draw straight lines like we teach all of our children to do, and not color outside of them. So I'm a cloud guy. This is from the Advanced C++ book back in 1991. Reality and nature are more like this. This is a picture of a C++ program. And you get underneath and you're down almost naked next to the hardware. And a good designer understands all of these levels in between, from the very highest down to the lowest. So this is C++. This is Eclipse. Now, there's kind of a nice thing about this Eclipse picture. It was actually one of the Eclipse guys who suggested this for me. This is a picture by Kandinsky. And he said, the reason I think of Kandinsky paintings is there's a lot of objects that complement each other and work together. And in that sense, Eclipse brings people together as different objects that are interacting and complementing each other's in different ways. And of all the people I asked about what painting would your model be, the Eclipse people were the only one to come up with a human metaphor. for an answer. And I'm really going to emphasize that today, that this is all about people, and we need to get people and human mental models into the process. Brand, this is rational rows. This is serious. And this, of course, is UML, lots of straight lines. All the diagrams in UML are straight lines, like we take our children to color. We'll come back to this picture a little bit later. The problem with drawing lines, or drawing lines around things, is that they create a partitioning, like I was creating that partitioning of the coins. And any partitioning of a complex system is necessarily imperfect. Nature has no parts. So you have a part that you call an arm. Well, where exactly does your arm end and your shoulder begin? And it's a system. And you have another system that cuts across this, which, I mean, several systems, your nervous system, your circulatory system. And so when we get out and cut a system into parts, we're losing information. And the partitioning can never be perfect. Now, I think we all know this, and anyone who's done modeling runs into this problem again and again. But we kind of seem to pretend that we can treat these independently, and the integration between them is only ad hoc. So there's really no reasoning about the model, and I'm going to try to avoid using the meta word, except once in this talk. But we don't have a good model of how our models fit together. And we pretend we can treat each one of these individually. And that, as I say, ends up being problematic later. So as a concrete example, I'm going to go through something called object-oriented programming, which probably none of you do. How many Java programmers? C++ programmers? These are class-oriented programming languages. It's almost impossible, it is impossible, to do object-oriented programming in Java. You can do it in C++, but it takes a lot of imagination. How many JavaScript programmers? There's my object-oriented programmers. They understand objects. They write objects. I mean, so this is, and you all say, JavaScript, what's he saying? Oh my gosh. Ah! No, I mean, this is real object-oriented programming and kind of the original vision that Alan Kay had for the model that in particular children carry around in their heads of how the world works. But we tend to believe there are these things called classes, which are neither necessary nor sufficient to OO. But as Brand said yesterday, some large percent of the diagrams that people draw, what did you say, 70% are class diagrams. Well, that's not the thing. That's like, I mean, if you're building a house, a good house or a clay model or wood model or cardboard model of a house is a good model. What classes are is they're either the blueprint at best, which is one projection, or more realistically what they are is the scaffolding around the house that you use to build the house. They're not the house. They're not the thing, and they're not even a model of the house. They're a model of the scaffolding we use to build the house. And then we have another view, which is objects. And those correspond most naturally to our mental models. And then we have use cases, which also correspond naturally to our mental models. And we'll go through this in a little while. So in our mind, we have objects and use cases as natural models. And one of the points I'm going to make this morning is that a model isn't something on a piece of paper or in a tool. It's something inside of a human mind. There is no information in any computer. There are only data. Information exists only when you interpret data, and interpretation takes place in the human mind. There's no information in a model, only data, except for the mental models, which Piaget, the psychologist, called operational models. And this is where object orientation came from. Now, somewhere along the way, we lost our way, And we decided we're going to create extrinsic models like classes and UML diagrams and things like this. And we've completely lost attention to what the UX people know very well, which are the mental models that people carry around. And as someone astutely noticed during the panel yesterday, the word UX appears once in the entire proceedings of this conference. And we call ourselves a modeling conference. So we have a very, very different view than Alan Kay did when talking about the mental models that children carry around, that he was talking about back in the 70s and maybe even back in the 60s. We'll talk a little bit later more about Christopher Alexander, who is an urban planner and architect, and is where we get the notion of patterns. I'm one of the founders of the pattern discipline here about 25 or 26 years ago. And Alexander wrote an essay called "A City is Not a Tree." That is, if you're an urban planner and you're trying to say this is Austin is a good example. By the way, Austin is a great city. Great jazz, great food, and it's not Texas. What he said is absolutely true. So go to Austin, it's a great place. But you'll see the neighborhoods, the parks, the urban district, the entertainment district, the restaurants, the university, all kind of blend into each other. And you can't really easily draw a line around the university community and distinguish it from, what is it, 6th Avenue, where all the jazz places are. They kind of blend into each other. And that's just a city, which is a pretty simple thing relative to the things we build in software. So, these are from Alexander's essay, "A City is Not a Tree." And he says that most cities end up looking like the one on the left. So the structure is a directed acyclic graph, a DAG, rather than a hierarchy. And it's difficult to properly do abstraction along a DAG. And so most of us who are building abstractions or doing partitioning are thinking of the picture on the right. And this loses information that's essential to grasping the complexity of a system. Alexander has this picture of the city of Cambridge in the UK. It has the same property that Austin has, is that the university and the city kind of blend into each other. So you look at a bar, we can go to get a pint, and you ask, well, is this part of the university or part of the city? And if you have that kind of urban planning view, the answer is, well, it's part of both. And so if you treat a bar with respect to the rules and regulations of the city, you're going to run afoul of the expectations of the culture of the university. And so you have to deal with the people at a much more complex level than a simple model like a hierarchy can give. And in general, this is particularly true of software models because we know software is so complex. Everyone is, in the early days of object orientation, a lot of the book authors were making class diagrams of zoo animals, right? So looking at the Linnaean hierarchy and classifying things. So Linnaeus was a Swedish guy. He grew up and worked not too far from where I live. He was up on the island of Gotland and up, where's the Danish guy here who's moving to Lund? I think he was actually living in Lund. But he made this model of how animals work. And you know what his criteria were? Which is how God was thinking of them when God made them in order to give them similar characteristics. So he was kind of on a religious mission. And we still, to this day, have the hierarchical Linnaean classification of animals. But if you look really at kind of the genetic structure, one of the structures that's used, and there are several, is this one. This is what's called a phylogenetic network, and it's produced by a modeling tool called split tree. And if you go down and zoom in here, it's not a hierarchy. It's a very, very, very messy graph. And so the Linnaean hierarchy is in fact not a good model from the point of view of some of the fundamental biological properties of the things we're classifying. And biology knows this. And then there's abstraction. which is discarding information, and the supposed benefit is to understand a system from this perspective and then another perspective. Someone who I've done a lot of work with over the years is Richard Paul Gabriel, who is a very interesting and strange guy. He's a lead guitarist in a rock band. He's an extreme biker. He has a Master of Fine Arts in Poetry from Warren Wilson College, which is kind of the place you go in America to get a poetry degree. He was a founder of a company, founder and CEO of Lucid, which was doing a lot of the Lisp stuff back in the 70s, and is one of the creators of both Scheme and of the Common Lisp Object System of CLOS, or CLOS. He's also one of the early patterns guys and an interesting writer. But he has this wonderful essay called Abstraction is Evil. And he distinguishes between abstraction and compression. So how many of you write poetry? Yeah, you're all engineers. Someone admits it and is willing to admit it. So is poetry abstract? Is poetry abstract? It doesn't have to be. No, it's not necessarily abstract. What makes poetry different than prose? It's compressed. Every word in a French poem means something more in that context than it does in ordinary French. Les sanglots longs des violons de l'automne blessent mon cœur d'une longueur monotone. I don't know what you do with la rima, la rima, la rima, la rima, quoi, la rima, rien. Anyone know that one? I've studied quite a bit of French poetry. It's compression. And what compression means, I mean, as engineers, we kind of know what compression is that we have some code that we use to look for recurrence of things and be able to represent some information with less data. Now, for a poem, the code that we use is our cultural experience and upbringing. For a good software program, it's our domain knowledge. And, I mean, complex number, is that abstract? Well, no, I could say, you're this complex number, you're this complex number, please add yourself. And you could add yourselves without me saying anything about real part and complex part. Why? Because complex number is a compressed concept of which you have a model in your head. It's not abstract. Good models are compressed, not abstract. So I'm really going to focus on this concept of compression. Now, compression allows us to be general without being abstract. And this slide is a little bit imprecise. And I'll talk later about the data context and interaction paradigm. But it's a general way of conceiving the world, or of thinking about how we model the world. And we model the world in terms of objects, the roles the objects play, the classes to which those objects belong, and the operational models or use cases of their interaction. And all of these are different models that we hold in different parts of our brain. And they're very general, but they're not abstract. For any given system, we can make a very precise enough that we can write a model of it and it compiles and runs. And I think that's what we're looking for, is to be able to put together multiple models like this that are not abstract, for which we need an explicit tool that's going to add the context, which we call model transformation. Well, where does the model transformation information come from? Well, another mental model. And now we have models of models being interpreted by models of models of models into models. So for model transformation, you have to understand at least 5 models. This is accidental complexity that arises from the very act of modeling. The model is there. It's in the human head. And there'll be a big man bites dog coming later in the talk. So we want compression, which is this relationship between data and information. No data, no information in a computer, no information in a computer, only data. Now compression allows us to talk about things simply. There's this joke that goes around where with this prisoner who went to prison and he was being led to his jail cell, and as he was going, the other inmates were saying things like 37, 25. They said, "What's this? What's this?" He said, "Oh, we're all sentenced for life here." And so these are jokes. We've been here so long that we know all of the jokes, and so instead of telling them, we just assign them numbers. This is compression. So one day he went up to a guy and he said, 16. The guy didn't laugh. 16. What's wrong? He said, it's the way you told it. One day he said 127, and everyone really, really laughed a lot. They hadn't heard that one before. So, compression should allow us to talk very efficiently, and a good language, be it a human language or vocabulary or something that's, that a tool understands, should have behind it the wherewithal to let us talk in terms of these compressions and to expand them back out into something that really runs. So we only need more data to the degree that models are far from our own mental models. So, we're computer scientists and we ask, can we formalize compression? And I was going to make these slides kind of the main focus of the talk. They ended up being more of a footnote. But I love this quote from Whitfield Diffie, which is, "We in science are spoiled by the success of mathematics." I mean, mathematics has been very successful. But mathematics is just a language. It is not reality. It is certainly not truth. I mean, just ask Gödel, right? We joke casually about completeness and consistency, and it's real. And so if we're going to talk about the limits of three balls bumping into each other, we need to be attentive to this. And this is real, and this shows up in macro phenomena in software development. This is what Agile is all about, is emergent behaviors, things that come out of the dynamics of the system that you cannot predict. And so I'm not saying to throw away mathematics, but I'm saying it's just a language. And so Klein says, mathematics has been advanced by those who distinguish themselves by intuition rather than by vigorous proofs. Now, I know it sucks, you can't get a raise. Well, you probably can get a raise for having good intuition, but you certainly cannot write a PhD thesis about something that's your intuition. And there's a really dominant academic value system here, which is, I need to show that I run the gauntlet, I can get a PhD, I can publish a paper at Models, and if I just come with my intuition, they're going to laugh me out of the room. But the great mathematicians are saying, this is the foundation of what's made mathematics great. So it's not like a proof is formally derived. I mean, the four-color map theorem proof took years and years of refinement, and when published was wrong and had to be corrected. These things go through iteration and feedback. It's not like the building of a model is a monotonically progressive, or, they don't just come from clean cloth. I told you I study architecture and builders. One of the other problems we have in computer science, at least for most of us who deal with digital computers, is that it ultimately comes down to 1 and zeros. You can't bend a 1, you can't cut a 0 in half. When you build a house, you'll maybe have a diagram or a blueprint like this, and it will say that this pipe comes up through the floor right here and comes out over here, and this pipe comes up here. Right here, exactly here, we will need a hole for the shower valve. Well, it's never right there, because you are never able to be precise enough for the variation in the width of the boards and the pouring of the concrete foundation and things. The nice thing about wood or plasterboard is that I just punch the hole in another place, and it doesn't matter. We can't do that in software. And so that's one of the things I think that's led us to this, this need for formality. So the pipes won't come out exactly where the blueprint says. And it's okay for wood, because wood is analog, but digital computers have to be precise. Okay, so that's the tutorial, and kind of a little background. I think a lot of people at this conference, if we look at history, the past, 200 or 300 years of history, it started with L'École des Beaux-Arts and then moved into several schools, including Jugendstil and the arts and crafts movement in the UK, and eventually into modernism and then postmodernism. And I think that, I was talking with someone who was kind of on the outskirts of this conference. They looked at the program and they said, if I didn't know any better, this conference could have taken place 20 years ago. What I'm reading in the program. I think we're kind of stuck in the modern school. And in the meantime, a lot of software, particularly in the industry, has moved on to postmodernism. So one of the things that I've become fascinated with over the past 20 years is something called design thinking, or the design movement. This includes people who you may know of, like Christopher Alexander, but a lot of other people who you may not have read. It's amazing how few programmers and computer scientists I run into who are aware of this major movement in philosophy in the 20th century. And I really like this quote from Bruce Archer in the UK, is that mathematical or logical models, however correctly they can describe the flexibility and interactiveness and value-laden structures of the design process, are themselves the product of an alien mode of reasoning. That is, mathematics is something outside of ourselves. It's a language we have evolved over millennia that's really not native to human nature. My present belief, formed over the past 6 years, is that there exists a designerly way of thinking and communicating that is both different from scientific and scholarly ways of thinking and communicating, and as powerful as scientific and scholarly methods of inquiry when applied to its own kinds of problems. Now, to kind of make a long story short, examples of this are things that people popularly associate with Agile. Now, there's a lot wrong with Agile, and I'm not going to attach that term to it. Though there's some overlap, I think it sets the wrong kind of expectations. But this whole notion, and what we find is crucial to design thinking, is that instead of starting with requirements and presuming that we can build a model from that's formal and completely consistent, pick your poison, and then from that build some implementation. The design movement says, well, we have enough experience that we have this hunch that this would be a good solution. Let's just try it. And now we get feedback. So I haven't heard anyone talk about feedback this week. Now, I know you all do it. You have to, or things simply wouldn't work. But we like to ignore it, and we like to pretend that we can point to the formal mathematical oracle that we have religiously followed all the way along, and so we have this thing that the more vulgar practitioners call traceability, and which the pseudo-academics call determinism or formality. And it's a myth. It's an approximation. Some myths are very powerful. But I think we get caught up in our own illusion, and we get caught up in the myth as being the reality rather than a demon that's kind of standing by our side and giving us some guidance. And we fail to let our intelligence take over when it can take over, and break from the myth when it makes sense to break from the myth. So methodology is a religion. And any method we follow, we tend to follow religiously. And if we don't follow it, if the model breaks, it's mea culpa, mea maximus culpa. I have sinned. I have not followed the ways of the model and of the method. And if it fails, it's not the model's fault. It's that we blame ourselves for not following the model. This is stupid. We're going to stop doing stupid things. I mean, the models that we talk about here are our own creatures. They didn't come out of nature. We like to believe they did with a mathematical footnote. But they're human inventions. And so, you know, we in programming have long flouted our ignorance about this. So there are some nice, really nice things that have come out of this postmodernism and design thinking. One of them is patterns. Another is the notion of aspects, which is more about concepts than about things. This is a kind of a central property of postmodern thinking, is we're thinking in terms of concepts. But we believe in their separability, and it's just not true. We believe that classes can be encapsulated. And we talk about encapsulation being a good thing. It's not. A system, as Brand said yesterday, is about a network of cooperating objects. If they're perfectly encapsulated, 100% encapsulated, they cannot interact with each other. So, I think we fail to distinguish between essential complexity and accidental complexity. And yes, we want to encapsulate the accidental complexity, but real complexity is going to violate encapsulation all the time. But we tell ourselves in our models that encapsulation is a good thing and that any coupling is bad. No, coupling is what makes systems systems. It's a good thing. But our religion tells us otherwise. And it's totally artificial. And the more we've striven for this separation, the more abstract the model becomes and the more distant from the thing we're trying to model. And then we lose fidelity by adding accidental complexity. So I think, you know, the train has come to the station saying, you know, postmodernism is here. We have this opportunity, but computer scientists have done, you know, some really horrible things with it. This is a quote from Christopher Alexander from The Timeless Way of Building. According to this view, a whole is created by putting together parts. So he's talking about kind of the classic modernistic view, that the whole is the sum of its parts. The parts come first, and the form of the whole comes second. And this sounds like oopsla, 20 years ago. All you need to do is take the right objects off the shelf and put them together, and you will have a system. And it was called reuse. But it's impossible to form anything which has the character of nature by adding preformed parts, like modular houses. Buy this bathroom module, this lobby module, this kitchen module, and put them together. You don't really have a home. You just have a bunch of walls. And the computer scientists never understood this. So even the so-called founders of patterns, this is from an article by Badinsky, John Vlasides, who was one of the Gang of Four, about a tool they had built inside of IBM. The tool lends itself to implementation with off-the-shelf components. And this is a patterns paper. I mean, it wasn't that they didn't read the fine print. It's that this whole paradigm of thinking in non-reductionist and holistic ways completely eluded this community. I mean, if you look at the Gang of Four book, there's not a single pattern in that book. And I tried telling them that when they were writing the book, and they said, yes, but the book is selling very well. And it took quite a few years, but eventually I got this mail from Richard Helm back in 2004 called A Confession and a Request. And he says, I finally grokked. Grok is from Heinlein, it's Martian. Means to understand deeply. I finally grokked generative patterns many years after he published the book, which everyone takes as a standard of patterns. He says, I finally got there. And I'm a little slow sometimes, but I got there in the end. So, I mean, Richard's a bright guy. Another bright guy who I always kind of found understood this with Eric Gamma, and there was recently some discussion on Twitter where someone talked about, oh, I know. I think LinkedIn asked me if I would endorse Eric Gamma for knowing something about patterns. And I thought, no, this is really funny. I posted it on Twitter. And someone challenged me and said, but you said there are no patterns in the patterns book. And I said, yeah, there's no patterns in there. But Eric knows what they are. I said, yes, what are known as design patterns aren't Alexandrian patterns. And some of them still don't know them apart. But Eric does. And Eric came back and said, well, Cope was a great teacher on this topic. So, I mean, if you think the Gang of Four book is going to give you the insight into this postmodern or design movement perspective, you're wrong. These guys were still stuck in modernism. The patterns were UML, for crying out loud, with straight lines. I mean, Alexander doesn't draw a straight line anywhere in his book. The straight line is ungodly. It's a human engineering invention and a pretense of formalism. And Alexander wrote to me and gave a talk at Uppsala in 1996. And this was eventually published in IEEE software, where he said, I would ask if the pattern languages in software have the tendency to make the program or the thing that's being created morally profound. Now this goes back to yesterday's keynote. We should be focusing on the great problems of the age, which come down to human relationship and organization. I mean, a lot of the climate problems we're having ultimately can be traced to public policy, and it comes down to are people working and playing well together? Morally profound. I have no idea whether the search for something that helps human life is a formal part of what you're searching for. Is it for the modeling community? Or are you primarily searching for, what should I call it, good technical performance, he said, cynically. So this is kind of chapter 2 of yesterday's keynote. I mean, there's a lot at stake here. And we as computing people touch so many aspects of human endeavor. We have a moral responsibility to be tapped into the human mental models, not just playing algebra with our computers. And this isn't just us. I mean, going into ecology, I mean, ecology has made this mistake as well. So this is from a paper that's more than 30 years ago about the Tennessee Valley Authority project, where they had models of how building dams along the Tennessee River in the United States were going to make it possible to do irrigation, to generate electrical power, and it brought new risks of water contamination, soil erosion, contributed to rural unemployment, depopulation, grave imbalances in global food markets. I no longer would have the annual floods that brought alluvial soil to refresh the soil, so the soil is starting to become impoverished along the banks of the Tennessee River. Why? Because the models were abstract. They were not complete. There's many ways of viewing how you build the dams along a river. Probably 10,000 ways, and they picked 2. And the result was a disaster. Why? There's a pro-innovation bias. We all think innovation was good, especially this crowd. I mean, most of us were probably around and can remember when the first man walked on the moon. And these were exciting times, and we believed in the triumph of technology. And I see the echoes of that in this conference. That technology and formalism and models will triumph. I don't hear the human being mentioned very much, or society. And here's just more from the same paper. So, can we build systems that implement deterministic models in this complex world? Yes, for simple systems. I mean, if you're building pyramids or you're doing basket weaving, things that they're so simple, as Whitfield Diffie said, that you can analyze them with mathematics. Right? The complex stuff happens in biology and in sociology. Mathematics is about the simple stuff. So for simple systems, yeah, I mean, we can build deterministic systems. But who are my Java programmers? Again, you know that Java programmers are non-deterministic out of the box. If you're using a hash map, the behavior of hash map and with an iterator is non-deterministic. It's in the documentation. It drove me crazy for several days. Filled up a hash map with some things and I was iterating over it, and I could run the same program twice in a row on the same machine and get different results. It's non-deterministic out of the box. Why? Because the world with which it's interacting includes the garbage collection system and the memory management system of the underlying Java virtual machine. And that ends up being different every time. So for complex systems, no. I mean, give up determinism. It's an illusion. Because of the ghost in the machine. And yesterday, we've seen these words come up in many talks: complexity, uncertainty, chaos, incompleteness. And the big ghost in the machine is a human being. For those of you who write programs that interact with humans, humans are wild cards. You can't predict them. And so to make any model of an automaton that's interacting with another system called a human being that's random and capricious and arbitrary is a futile exercise. So the good news is, so you're all probably depressed about this, the good news is, if you're doing this right, it really doesn't matter. So good UX people know, but I don't know if there's any here, if you have a modeless interface with buttons on it, it doesn't matter what order you fill in the forms or push the buttons on a given page. It simply doesn't matter. Or if you're using a hash map correctly, it doesn't matter what order the things come out in iteration. As a mathematical object, that ordering is, by definition, undefined. And it's your mistake if you're depending on it. So I think there's a lot of arbitrariness and randomness, but we shouldn't confuse that with inability to make systems that do what they need to do. So determinism is neither sufficient nor necessary. And in fact, for the kind of systems we build that interact with the real world, it's impossible. So what are the design thinking principles that come from this design movement? Number one is learn from people. No one has ever said, our project succeeded because we used UML. UML becomes the talking point that brings people together to have the conversations around the whiteboard, and it's the conversations and the exchange of ideas that make it successful, not the tool. So the models have value, yes. The tool has value, yes. But it's just an enabler to the conversations that take place. In Agile, we say individuals and interactions over processes and tools. So UML can be an enabler for the discussions behind successful projects. And it's learn from people. And by the way, it's not the average person, but it tends to be the extreme people. Find the outliers, because they're the ones who are going to give you some new, useful knowledge. And the average person, anyhow, doesn't exist. There is no average person. Complex phenomena have interesting data in the tails of the distributions. And you're going to get these by looking at the outliers, rather than kind of modeling the average and making an ordinary stochastic model or statistical model. We want to facilitate this social interaction at all times, because many perspectives are going to help us explore the dark corners of the design and give us feedback and correction. And we want to make it tangible through things like prototypes, through things like set-based design. Set-based design means let's have a bake-off. Let's build 5 different versions of this and then see which ones are the best. And then we'll pick. Toyota does this with designing cars. Honda does this with designing cars. Large telecom manufacturers that I won't name are doing this in building systems. And there's kind of a moral question here, because they kind of pit organizations against each other. And there's kind of a winner and a loser. instead of artificially asserting that this model tells us the right way to go, let's just try something that might work, get feedback, iterate. This is design thinking. And iterate relentlessly, which goes along with this. The examples that I've mentioned include patterns, but not the gang of four patterns, and especially pattern languages, especially in HCI. There was some brilliant work that's been done by a lot of the HCI people very early on, where they really understand patterns. A lot of the rest of the pattern community just isn't there yet, because they've kind of fallen along in the lines of, like the slide of Badinsky and Lucides that I showed earlier. They're still modernists, and they're still talking about patterns in terms of being UML diagrams. Well, there's another one called object-oriented programming, and that's what I'd kind of like to dedicate the rest of my talk. It's actually quite a postmodern notion, because it's about concepts and mental models that come out of Piagetian psychology, which Alan Kay was using to try to understand how to build teaching machines for children. And then the nerds got hold of it, and it became Smalltalk, and Smalltalk got classes, and Simula also actually earlier had classes, and then C++ came along, and at that point it was dead. Because a C++ program is not, a program is a model. And I really like what Ed Lee said on Monday. A program isn't an implementation. The implementation is a thing after it comes out of the compiler. A source program is a model. A C++ or Java program is a class model. It is not an object model. A JavaScript program is an object model. Now, we have more than just those two things in our head, too. Alan Kay said that knowledge, particularly in the young child, is retained as a series of operational models. Models exist in the mind, each one of which is ad hoc and need not be logically consistent. And we need extra logical strategies to deal with these. Now, here's a picture of a girl out on the grass under a tree doing some work with a design tool. When is this picture from? What do you think? Who said it? Yeah, it's actually right. 1972. That's an iPad, for crying out loud. This is 1972. Now, this is actually what Alan Kay called a Dynabook, which was a machine he was building for teaching children. And it was to be an extension of their senses and mental models into the world around them. And this is where Smalltalk came from. Smalltalk was the language they used to program this to extend their mental models in the real world. And he says, we feel a child is a verb rather than a noun, an actor rather than an object. It's not a scaled-up pigeon or rat, like a lot of the program learning people were talking about. But he's trying to acquire a model of his surrounding environment to deal with it, and we'd like to hook into those and use her or his model rather than giving him or her one of our own. Model exists in the head, not on a piece of paper. So this is from Alan Kay. So we want to get at that model. It's not something we build on a piece of paper. So this is exactly what we're trying to do in DCI, is we have this child, and the child is acquiring models of the world around her. So she'll see a compass and kind of stash that away and know what a compass is for. And something to scan the horizon, and we'll compress these elements into some concept, and then similarly do the same with things like globes and maps, and store that away as another concept. And these get stored away in the right brain. The right brain is very good at massive parallel processing. It's not very good at sequential processing, but good at remembering and associating. Now the child learns how to use these to navigate, but in general learns how to use a navigation tool with a map-like tool through some set of steps through some operational model, which we'll call a use case, and those get stored away as roles. And those tend to be stored away in the left brain. So when we did the exercise yesterday about, do you have 2 accounts in your bank? This is what I was trying to get at, is this operational model inside someone's head that they carry around in terms of the roles that different accounts can play. So the roles are things for a money transfer, like source account and destination account. And then different kinds of accounts can play those roles. But the mental model we carry around is at a highly compressed level. Then we do design. We're actually going to use these things to write a program or to navigate the globe or to make a transfer in our accounts. And we bring these things out of our memory and associate them to whatever concrete instance we're interacting with at the time. So maybe I have a map at hand and a compass at hand. Both of these can play those roles, and the roles fit into this use case, which we then enact. So this is how human minds work. This is how Kay envisioned object-oriented programming working, and this is how DCI works. So, as I said, a Java program, it's data, context, and interaction. DCI. A Java program is a class model, an object model, and a use case model, a DCI program. A Java program is just a class model. The program is the model that is going to generate an implementation, but there's no modeling before that. The modeling happens in the child's acquisition of knowledge about his or her environment over time. The problem with classic object orientation is there's a concept missing, because we haven't gone into the mental model, we didn't listen to K, and the missing entity here is called a role. Now, we can kind of fake it in UML, but it's a convention for drawing straight lines in a certain way. And then we eventually created a stereotype called an actor and a stereotype called a role, but those are kind of sidecars, right? The other thing that's important here is we have time and space in one model. And in the end, this is a very postmodern concept. And what patterns is all about. Recurring sequences of events form patterns. So this pattern view and this DCI view and a lot of the design thinking views incorporate time and space together in a multi-dimensional mixture of models. Now, I've created a programming language called Trigve where I can write these operational models, I can write the roles, I can write the classes, and these things come directly from end-user mental models. I mean, it compiles and runs. So there's no abstraction here. It's just compression. Building a tool that allows people to express their compressions in a model. What's curious here is what we're doing is we start with a reality, and then we create a model of it in our heads. What Alan Kay said is we have the model in our heads, and from that we create a reality. Software development is reality construction. It's not that there's an extrinsic reality out there. We're creating new realities all the time that satisfies some mental model. So, in wrap up here, what are the things I've learned from DCI and kind of 45 years of writing code? Number one, we're often more creating a reality than modeling some supposed reality. Number two, it's about people. We want to get stuff from people more than from artifacts or from tools. Number three, the model should nonetheless be closely linked to the built and evolving artifact. I see no need for the difference between the modeling language and an implementation language, because we want to use compression, and compression should be enough to get us there. And formalism has value only for things that remain constant under emergence and under complexity. So what do I mean by creating a reality? This is our horse, Fruin, back in Denmark. And the picture is inspired by Henry Ford, who said, if I'd asked people what they wanted, they would have said faster horses. So he could have built a model of transportation which was based on horses and built a faster horse. Instead, he created a new reality. This is probably my favorite book in the world. And it's getting rare. I think you have to spend like 170 euro to buy it these days. And every new reality is new. And we try to use generic tools like UML. So, we have our lines, and we try to use those to describe something. Now, I'm sure the artist intended this to represent something. And there's something in the artist's context that allows the artist to see something here. And maybe you can see something here because the lines play tricks on your eyes. The French have a great word for this. It's a schmilblick. Right. But this is the problem, is that modeling languages don't bring enough domain context to bring understanding. It's just straight lines. And with apologies to the speakers, I'm sorry, I couldn't help it, but it's all about maintaining straight lines. We saw this talk a couple of days ago. That was a lot of the purpose of their environment. We need to be human-oriented. Information exists only in human minds, and therefore models exist only in human minds. What's in a tool or on paper is a representation of that model. So we want models with people as input and output. It's something to come around and talk about, and it's the talking that's important. It also needs to be updatable as slow hunches arise. I need to be able to turn these things around. And a lot of this is about understanding the psychology of things like slow hunches, psychology of perception, and I'm hoping that next time I come back here, there's going to be a lot more talk about psychology rather than technology, because that's where models live. I couldn't help put up this quote. This is kind of, I think, the root of the problem. That models are all about things in our head, and we don't understand. Now, we don't understand. UX people do. Psychologists do. There are people who make a living of this, and so we need these communities to come together, as was talked about in the keynote yesterday. It's not about automation. Toyota has discovered that it's not about automation. Toyota is pulling the robots off of its assembly lines and replacing them with people because robots don't learn. And this is about feedback and getting better all the time. And Toyota has discovered that the robots get them stuck behind the competition. They should be close to the artifact. And the big recommendation I'm going to make here comes from Tridvi. A modeling language is what the language designers omitted to include in the programming language. So we don't need modeling languages. We need proper programming languages. And I think the right direction here is going to be domain-specific languages that are going to pull more of the compressed mental model of the person into what we express in code. Someone here used C++ as a modeling language. Bjorn Strostrup created it with that in mind. That was the whole idea. That's the whole idea. And it was feedback from the audience saying, oh, but you're just programming, it's not modeling. My gosh, why are you making this distinction? Bertrand Meyer talks about people who create models and not code. He says there are people who love to create models, bubbles and arrows, because bubbles and arrows don't crash. Sure beats working. Fidelity, I want fidelity in all properties, not just the bubbles and arrows. It has to be able to crash. And that means I'm going to make mistakes. We learn from our mistakes. Personality or identity, the whole process comes from learning and from failure. There's an old architectural saw from a Chicago architect that says that form follows function. It's not true. I like Petrosky's view. Form follows failure. The whole purpose of a model and its value comes from failing again and again and again, so we learn something. Formalism, again, this is for the simple stuff. So simple it can be reduced to mathematics. We do not have a software physics that we can appeal to. We know we cannot have completeness and consistency. Systems are intrinsically ad hoc and intrinsically inconsistent. And software engineering is not engineering. I know, I'm an electrical engineer. I know engineering when I see it, and software engineering is not engineering. Engineering is rooted in science. And we're rooted in kind of a pseudoscience or a very anemic science. We need to be rooted in a psychological practice based on empirical feedback. So I do some modeling now and then, but it looks like this. These are folks using Legos. They're building software models. These are models of their programs. And of course, it's not the model that has value. It's what's left in their head and organized in a new way after they put these Legos together. So this is a program. Whoops, sorry. This here is a program. I don't remember exactly what this one was. He told me. Last slide. Models are all we have. Mental models, UML models, C++. It's all we've got. A model is a model is a model. We need multiple interworking models for complex issues. A serial design path to multiple models or overly abstract models just adds accidental complexity. Abstraction is evil, including isolated partitioning. And compression is really golden. So models are an aid to play. You all got one of these in your package from our good friends at the ACM. And it contains 2 pens and a ruler for drawing straight lines. I want every one of you to take this out of your packet right now and either break it in half or commit to giving it to your children when you go back home. It's not about drawing straight lines or coloring within the lines. It's about the complexity that makes us unique as human beings. It's a form of modeling. There's a whole form of postmodern modeling that we can bring to the forum here. And I hope to be talking with you more about that in the future and next time I see you. That's my message. Thank you very much. You have a great day at the rest of the conference.
Thank you very much, Jim, for this inspiring talk. Questions from the audience? Peter.
Thank you very much for your talk. Now, you said that we all have our different mental models, and these models are compressed. This means we bring our own history, our own feelings toward the models. How do we then communicate with other people using these mental models and reduce the extraneous load that will come when we want to get over our idea?
Oh, excellent question. So, first of all, I'd like to point out that a lot of our models come from the culture in which we grew up. So our culture and our experiences shape our models. Now, most cultures offer some large level of shared experience, and it's that shared experience and then just, the words that we have learned to attach to them that enable some basic, level 2 protocol of communication. Then we start building on that. Right? A great analog for this is a keynote that Guy Steele gave at Uppsala, and it was a brilliant keynote. I was there, but I knew it was coming. So he got up and he said, most of the time I do not read my talks, but I will read this and you will know why. I think you all know what a man is. And I was like, what the heck? hell is going on? And by the time he's 45 minutes into the talk, he says, what I have done is I started using single-syllable words. And if I needed a multi-syllable word, I would define it in terms of the single-syllable words I have already used. He said, this is how we program in Java. And we need to stop doing this. But I mean, there is something fundamental about this to human communication. We keep building up. And in a community of design, you can start building a design vocabulary. Now, in domain analysis, we call this a domain dictionary. And in fact, Gertrude and I were just talking about this morning. It's critically important to have a shared vocabulary that's explicit so that everyone knows what page we're on. And this is something that kind of eluded the UX panel here yesterday. There was the one guy down in the end from Ericsson who really got this. Words mean things, and it's so important. But human processes are very good at building meaning.
Thank you.
I'm honored to have a question from you.
Thank you. Well, first, kind of a comment, because I wanted to comment on your distinction between class-oriented and object-oriented programming, which I think is important. I wanted to mention, which you may know, is that there actually is a large part of UML that has to do with role collaboration modeling, which was heavily influenced by Trygve.
Yeah.
And in fact, there was a standard that was done a few years ago for service-oriented architecture, which large part of it was about treating a service-oriented architecture not as a software model, but as a model of interactions between consumers and producers and a collaboration with different roles. And it all worked out how to do that at both an organization, human, and software level, and almost no one uses it.
No one uses it, I know, and it's kind of a puzzle.
Yeah,
right?
so, I mean, I'm almost given up. Because,
I know.
And just kind of given in, because even in the software, the SOA community, they just went back to what IBM put in the standard, which was, oh, it's just components interacting through APIs.
Right.
So how do you break through that? How do you get people to think?
So I've been pretty good in my career at building the community. So I helped build the pattern community and a lot of the early object community through the advanced C++ work. And now what I'm trying to do is we're trying to build this DCI community around Trygve's ideas. And, you know, I hope we work up to like a conference. We have an active mailing list. The active work I'm doing right now is I've just created this new language called Trygve. It's on GitHub, it's public domain, it's free, it's open source. If you want to play with this stuff, I'm trying to build a community. I don't know if it will happen in my lifetime. This is a big, big, big change. And big changes happen slow.
Well, it's interesting because, like you said, we naturally think about objects. It's a big change because we spent the last 50 years training ourselves not to think naturally.
Yeah, don't think about elephants, right? And
I never think about elephants.
Right. So we have a big job here to do, and what I'm looking for is help from this community, because I think the current perspective of this community is much more closely aligned with the class perspective. And if we can get more people thinking in terms of object models and carrying this all the way into human mental models, operational models, getting the human being involved and not just a tool, right, and doing some real psychological digging into people's heads, there's a great opportunity in this community to move this idea ahead. But it's going to mean getting out of the comfort zone of sticking my head inside of my monitor and just working with my tool. It's going to take workshops, you know, working with people and learning some of the skills that UX folks and psychologists know to get inside people's heads. And it's hard work, it's subtle, it's fun as hell. It's great working with people.
Thomas?
Hi, so I agree it would be stupid not to learn from nature, but don't you also agree that humans manage to do one up on nature? For example, the wheel. It's a quote-unquote ungodly thing, isn't it?
But the wheel?
The wheel, yes.
Apples roll down hills. It's one of the ways they
that's not a wheel. Come on. An apple doesn't transport anything. An apple is an object that moves right? But
Apple transports
nature
seeds.
did not invent the part wheel to achieve a goal, right? So
True.
What I'm against is a demonization, and I think it's even there on the slide when you say abstraction is evil. What about if in the jail of people that use abstractions, which you seem to suggest that they all belong there, right? The people who use abstractions, they should be in a jail, but they can tell 1,000 jokes at one time by using a number. Whereas your compression people can tell one joke at a time.
No, it's just a high
So
level.
that's what we need for tackling
no.
complexity.
First of all, I think
let me finish one more thing I want to say, and then I'll shut up.
okay.
You quoted Whitfield Diffie, right?
Yeah.
I think he would still be hopping from one boot cloud to another if it hadn't been for the mathematicians who provided the straight lines that give us the actual means to do public key cryptography. Diffie did not know how to do this stuff. He had it would be nice to have idea, but it was necessary to have the mathematics to do it.
Okay, that's
Okay,
fine.
so let's not demonize here. I understand that exaggeration is a point, as a tool to make a point, right? But I'm totally against this black and white issue and saying, okay, we have to leave the terrible past and move on to the glorified future. Okay, thank you.
So, first of all, I think you misunderstand compression, and all I can say is do your homework. The one number that can stand for a lot of jokes is still compression, it's not abstraction. Secondly, yes, we do stand on the shoulders of mathematicians, but mathematics, physics, and biology are artificial human creations of ways of dividing up knowledge. So, computing science also stands on the shoulders of biologists and of physicists and of just about everything else you can name. Why do you happen to choose to pick mathematics? Why does a dog lick its genitals? Because it can. And if you want to pick something simple, oh, let's pick mathematics. I do that because I can. And then I can ignore all these messy things. And so we like to pick mathematics because I can manipulate it into a PhD. And I can formally argue it to the anal appreciation of those who look at things that way. And I think that's more the history of mathematics, particularly in education. I mean, I've been a professor at several institutions, and there are some, you know, at Fayou Bay, where mathematics, okay, it's a tool, it's a language, great. And there are some who spend all of their time deriving everything from mathematics, which is just, we're going to reduce everything to this one abstraction. And it's pure hierarchical thinking, and it's just ignorant. It's ignorant of the history of computing, it's ignorant of what mathematics is. So, no, I think this is a paradigm shift, and it's important to be able to see things from the other side, but it's hard to do that unless you've actually worked on that side. And that's why I said, you know, I think that it's going to take 10 or 20 years for me to come back here and see this kind of thinking and these kind of objections die out. Let's buy each other a beer later. Let's share a beer later. Other questions, or are we done? Coffee time?
The comments? Okay.
I had a great time here. Thank you for your attention. And Godspeed. Have a great trip home and a great rest of the day.
Thank you. James.